Here's video 3 of chapter 5. So we just left off at type 2 of the calorimetry problems. What I wanted to go ahead and say before we looked at the third was over here on the side, I tried to indicate the difference between plain old Q and delta H. So Q is just heat, and it's going to be just in joules or kilojoules. Delta H is always referring to some kind of reaction or process. It's known as enthalpy, and it is going to be in kilojoules per mole. So you're always going to have to take your joules, make sure you get to kilojoules, and then you divide it by whatever moles of a substance you're working with. We'll see that again in the type 3 here. Type 3 is when you're dissolving a salt into water, so dissolution. It's similar to the last problem where we're working with a full solution here. And when you dissolve something, it can be endo or exothermic. Once again, it's going to act like a mirror. So we're going to watch the water and see what it does. If the water's temperature goes up, that means the water has absorbed energy, and therefore the salt must have released that energy. Or the opposite, if the water's temperature goes down, that means the water lost energy. The water can only lose energy if the salt absorbed energy and it took in energy when it dissolved. So let's try to look at an example. When 10 grams of ammonium nitrate dissolves in 100 grams of water, the temperature drops from 25 to 18. So what we want to train our brain is to go ahead and start thinking about what does that mean. If the water's temperature went down from 25 to 18, did the water gain or lose energy? It lost energy, right? If it lost energy, that means the reaction or the process must have stolen that energy and absorbed it. So right off the bat, I now know that this is an endothermic process because the water lost energy, which means the salt must have absorbed it. Now our job is to figure out how much energy was transferred. Again, we're assuming the specific heat of the solution is the same as water. So we focus Q of solution here. Whenever we're working with water and a salt, the way we're going to deal with it is we're going to take the combined mass, so 100 grams of water, 10 grams of ammonium nitrate, and make that our total solution mass. It was told to us that the solution is going to have the same specific heat as water, and the solution's temperature is -7 degrees because it went down by 7 degrees. So our Q here turns out to be -3,221 joules. Once again, if the solution lost energy, the salt must have gained energy. The process, when it dissolved, gained that energy. So we now know that the Q of the salt, how much energy did the salt take in? It took in the 3,221.68. So it's an endothermic process. And lastly, all we need to do is get into that kilojoules per mole. So we take our joules, we convert it to kilojoules by dividing by 1,000, and then we divide by the moles. Well, this time we weren't told the moles, but we were told that in this scenario, 10 grams of ammonium nitrate were dissolved. We don't care about the water because it's the salt that's being dissolved. So we focus on the fact that 10 grams of salt was being dissolved. We go to the periodic table and come up with his molar mass. We add his formula up, divide, and we get 0.125 moles of ammonium nitrate. And then we take our kilojoules and divide by the moles so that we end up in kilojoules per mole. What this means is that 25.8 kilojoules is required or absorbed every time 1 mole of ammonium nitrate gets dissolved. So it means if I doubled the moles, I would also double the heat. So that's why this ratio is really helpful. Now here I technically probably should have gone to 1 sig fig because of my temperature way up here. Tests are going to be multiple choice, but I won't try to trick you too much on sig figs, but we do want to try to follow the rules, and Mastering Chem will tell you when and how many sig figs, when to pay attention to it. So we want to get in the habit, and this really should have been rounded to 30 kilojoules per mole for 1 sig fig. So those are the 3 types of enthalpy problems you'll run into with calorimetry. All 3 of those will say calorimetry in them. Because here we're going to be moving on to lots of types of calculations for enthalpy. So we've got to be able to put them into categories. The next type is using what's called Hess's law. So Hess's law will help us find the delta H of reaction. Remember, the degrees still means standard temp and pressure. which is usually 0 degrees Celsius, 1 atmosphere pressure. And it can help us estimate and figure out the enthalpy of a reaction. So the way we're going to do this is we have to apply these couple of rules here. If you take an equation and reverse it, we already saw this, then you have to take the enthalpy change, the delta H, and reverse its sign. So make it positive or make it negative. Also, when we put these different equations together, we can cancel anything that shows up on both the left and the right side as long as they're identical states. So if we have liquid water on the left, it can cancel with liquid water on the right, for example. And then when we're working with coefficients, if we multiply or divide all of the coefficients by a number, then you also have to do the same thing to your enthalpy change, to your delta H. You also have to multiply it by 2 or divide by 2, whatever you did. And then you add these together to get the overall. I'll show you an example. So Hess's law, it'll always look very similar to this, where you are given an overall reaction. So that's this bottom one here. And it says, given these two reactions here with known enthalpy values, they're given it to us, calculate the enthalpy of the third. So what you do is you manipulate the given ones to get to the final. So the first job is to figure out whether you need to reverse your equations or leave them the way they are. You're trying to get them to match the final. So here in this top reaction, I just choose somebody that only shows up one time. So you see how KCl only shows up one time in all of these given reactions? Well, KCl has to go on the left because in my final equation down here, that's where KCl is. So automatically this top reaction needs reversed. So I make my little note here that I'm reversing it. And what that means is I have to take this negative 203 and make it a positive. So I recommend rewriting them in the correct order. So what I did was I rewrote this equation backwards. It now has coefficients of 2, but I'll talk about that in a minute. All I've done so far is reversed it and made my negative 203, I've made it a positive. Okay, the second reaction, I'll see H2SO4. He only shows up one time up here, and I need him to be on the left because the overall equation has him on the left. So that means that second reaction is going to stay the way it is. So I prefer to rewrite it, but just leave it exactly as it is and leave the delta H as it is. Once you have them in the correct order, you can move on. One substance that I would not have paid attention to is something like water here, because do you notice that water is showing up multiple times? KOH is showing up multiple times. They're not going to help you as much. You look for a substance that only shows up one time so you absolutely know whether it needs to go on the left or the right. Okay, so I have them both in the correct order because once again, I'm trying to get them to match this last equation. Then I start looking at the number. So you'll notice I only had one KCl to start with and I need 2. So that means I'm going to need to multiply this entire reaction by 2. So you multiply every coefficient by 2 and you also multiply his delta H by 2. Then I notice the H2SO4, that one looks okay because I only want one H2SO4. So then I start seeing if things will cancel well. So remember, you can only cancel things if they're on the left and the right. And what you're doing is you're combining these two equations. So you'll notice there's 2 liquid waters on the left here, and there's 2 liquid waters on the right here. So those 2 cancel. There's 2 KOH solids on the left, 2 KOH solids on the right, they cancel. And then you bring down anything that does not. So you've got 2 KCl, you've got an H2SO4 left over, you have 2 HCl's and a K2SO4. And then the final step is to then change your delta H's however you needed to, based on if you reversed them or if you multiplied them, and then you add them together. And when I add them together, I get 64.8 kilojoules. So this was an overall endothermic reaction. Okay, another example, we're given 2 again. You can be given more than 2, but you're given multiple reactions with delta H's, and you're looking for an unknown. So the first step again is trying to figure out whether you need to reverse things or not. You notice there are lots of N2s and O2s. I would not pay attention to those yet. I would find things that show up one time, such as NO2 gas. Okay, well, where do I need NO2 gas to be? in my final equation, it's in the right side. So that means I'm going to leave that top reaction the way it is because I need NO2 gas to be on the right. So I rewrite that equation as it is. I keep its sign and everything. NO gas, however, needs to be on the left side in the final. So I'm going to have to reverse the second equation, and I reverse it just as it is, and I take its positive 90 and I make it a negative 90. Then the next thing we do is see if anything means multiplied, or maybe things are ready to cancel. So here I only need one NO, that looks okay, and one NO2, that looks okay. So I'm not going to multiply anything yet. I'm going to look for cancellations, and you'll see that 1/2 N2 and 1/2 N2, they cancel, and you're left with NO plus 1/2 O2. Let me explain this one. There was one O2 on the left and a half of an O2 on the right. Well, they are the same substance, not the exact same amount. So if you'll notice, a half cancels from this side and a half cancels from the left side, and that means 1/2 is left over. And then the NO2 comes down. We notice that this matches perfectly our overall reaction, so we did it correctly. And then you add your delta H's that you came up with. So you get negative 56.6 kilojoules, and that is exothermic. Another third type of problem we can run into, so we've talked calorimetry, we've talked Hess's law, and now we're talking enthalpies of formation. And enthalpy of formation is how much energy is required to produce or make 1 mole of a compound from his constituent elements in their elemental form. So for example, if we're trying to make sodium chloride, 1 mole, you would take 1 sodium, and so sodium comes as by himself. Chlorine is a diatomic gas, so he has to come as Cl2, and you're making NaCl. You're only making 1 mole, so then you have to balance it accordingly. So to get Cl2 down to only 1 to match the right side, I'm going to have to put a half there. I didn't get to look up this formation number here. There is a heat of formation appendix that I'll post on Moodle under this chapter, and we could go look for his value there. What we want to understand at the moment is how to come up with this equation. So for example, write the equation that represents the enthalpy of formation of NH3. So you're forming a compound, and you have to only be making 1 mole of him. Okay, so you've got 1 mole of NH3 from his element. So you think, what is the elemental state of nitrogen? Well, he's a diatomic, so he comes as N2. Hydrogen, his elemental state is also diatomic, so he's H2. And then you've got to get these to match the right side. So you only need 1 nitrogen, which means you're going to put 1/2 here, so that 1/2 times 2 gives you 1. And then you only need 3 hydrogens, so 3/2 times 2 gives you 3. So now the 2 sides are equal, and we could also go to that appendix again, it's in your book as well, and it would give me the heat of formation, how much energy is required to make NH3. Heat of formation can be 0 for elements in their elemental state, and we want to know this. So any element that is in his normal elemental state has a heat of formation of 0 because it requires no energy to get there. Solid copper is already solid copper, so it takes no energy to form him from his element. Same with oxygen gas, solid iron, chlorine gas. So the way we use these values is by this equation. We take the sum, that's what the sigma is, that looks like an E, the sum of all of your heat of formations of products minus the sum of your heat of formation reactants. The N and the M are the stoichiometric coefficients. So when you have a balanced equation, you'll use these. So in this example problem, you have 3 CO2s. So you take 3 times CO2 heat of formation plus 4 of the liquid water heat of formation. Those are your products minus your reactants. You only have 1 C3H8 and you have 5 O2s. And O2 is in his elemental state, and so he has a value of 0 there. And then we do products minus reactants.